So this short video here contains a simple example how to apply a different kind of static scheduling technique called software pipelining. So once more, here we have our friend, the simple example, where we have the two read after write dependencies in the code, which made life miserable for us before we started optimizing the code. In this implementation of this assembler code here, there is a correspondence between each loop in the source code level and each loop at the assembler level. So first time you go through here, I equals 1, next time I equals 2, and so on. And it's a good correlation. However, is this really a requirement? Is there any way we could have scheduled these instructions such that we don't have instructions from just one iteration in the same loop? And I'm not talking about loop unrolling here. I'm talking about in a single loop with these many instructions. And that such a trick is solution is what's called software pipelining, where you try to do away with these kind of dependencies, and you do that by mixing instructions from different iterations into the same loop. So here, once more, we have the instructions, the load, add, store, sub, and branch from one iteration. And what we're going to do here is to stagger the start of each iteration on this slide. So iteration 1 starts one instruction further down. Then we're going to try to figure out which instructions we need to schedule together in the same loop. Here we have chosen 5 instructions, but 5 instructions from completely different iterations. And our intention here is to put these instructions into the same loop. The following loop, we would choose 5 new of these instructions to schedule, but now we're going to move forward in the staggering, and we're going to start doing the branch of iteration 1 instead of branch of the iteration 0. So this is a way of looking at what software pipelining is. We are going to pipeline the software sort of between the different iterations to once more to pull the data dependencies as far away from each other as possible. Looking now once more at this loop, and we're looking at the 3 what I call the active instructions, the one that actually performs the work here, the load, the add, and the store, load, add, store, and so on. So in the blue frame, we have those instructions for iteration I. And then in the green frame, we have it for iteration I plus 1, and of course the red frame, iteration I plus 2. What I would like to do now is to take the last instruction of the first iteration, the middle instruction of the middle iteration, and the first instruction of the last iteration, and I would like to schedule them together in the same loop. So here you go. So now I created a sort of a backwards loop here. You know, this is a load, add, store, while when I weave these instructions together, I have a store, add, load instead. And have to, of course, play with offsets in a little bit. So you may, for example, want to pay attention to this I minus 16. So what does this I minus 16, what does it mean? Well, if I'm going to execute this in the same loop, I know that the x sub I plus 2 is going to have an address which is 16 lower than and the x sub I element. So now, since I want to mix the red instruction from iteration I plus 2, I have to take that into account, and I have to. So this is actually what this minus 16 is. What really identifies that this instruction is from the red iteration and not from the green or the blue iteration. So now scheduling these instructions like this into real code would look like this. So we have the store from iteration I, we have the add from iteration I plus 1, and we have the load from iteration I plus 2, and then we have some way of to figuring out if we need to loop back again in the loop. Once more, we assume there is some prologue and some prologue and some epilogue, not prologue, epilogue code that will do some kind of setup and cleanup for the first couple and the last couple of iterations in the loop. But apart from that, we're just going to execute these instructions. So an interesting question here, staring at this code, is where are the read after write dependencies now within this loop? And maybe a little counterintuitive when you stare at this code, but it turns out that the dependencies that you have, there's one dependence from instruction 2, but that dependence goes to the very next iteration of the loop. This is where you write that register, and up here is where you read it. There is no more usage of F4 further down in this loop here. So there is a read after write dependence, but it's not within the loop. It's to the next loop. Also, the dependence from the load instruction goes to the next loop. So after this so F0 is written here, and after that nobody is even accessing F0. It's first after the whole iteration goes back here. So that means that what we've done here is we have no read after write dependencies within the loop. So we pulled everything at least one iteration apart from each other. But we still have quite a lot of write after read dependencies. And while you may still think that these are completely harmless, because they are harmless for the kind of architecture we are talking at, we will have to go back and talk about what we can do to overcome these dependencies, because it turns out that these dependencies will also harm our instruction level parallelism. So what you see here is, well, if it's 6 iterations per loop if you don't manage to fill the delay slot. Actually, I think you can move down the load instruction to the delay slot here, so that make it 5 cycles per iteration. It's not a new world record. The loop unrolling had 3.5 cycles per iteration. But on the other hand, the loop unrolling, even for this simple example, needed 8 floating point registers, while this implementation up here only needs 2 floating point registers. So if you have a more complicated loop body that needs more floating point registers, the loop unrolling may not be feasible, and you may want to do something like this instead. So summing up software pipelining, it's sometimes also called symbolic loop unrolling. It's in this simple example, it's fairly easy to understand how it works, but for more complex code, it gets more and more tricky to figure out exactly how to schedule these instructions. One advantage of software pipelining is that it has much less code expansion than unrolling, and it's very register poor. And actually, there's a technique called register rotating we're going to talk about later on in this course that can be used to make the usage of registers even more efficient. So finally, this has been 2 videos about how to schedule instructions pretending we are compilers. We're not, we are architects, but we still need to understand what constraints there are in the compiler world, and better understand what we as architects can do to work together with the compiler people and make sure that we can provide the right abstractions for the compiler people to find even more independent instructions. Because we don't have enough independent instructions. That often what stops the execution. Compiler optimization really helps us find independent instructions, and independent instruction is going to be the key to better performance moving forward. So ILP, instruction level parallelism.